So what we're going to do now is we're going to take a look at logical reasoning. We've looked at logical equivalence. That is that the idea that two statements or two propositions are logically equivalent when it is the case that for every value of their truth proposition, the truth table ends up being true or ends up being identical for the two propositions. Those are going to play a role as we go through and we prove the equivalence of statements, and as we prove the validity of arguments. But where we want to start is we want to start now to talk about what it means to have a logically valid argument, because logic really does depend upon stringing together these logically valid arguments, okay, into new arguments, and that eventually becomes the basis for math, okay? And so mathematics, and then inevitably it becomes the basis for computer science and the writing of programs. So the first thing we want to look at is we want to look at this idea of what it means to be a conditional argument to be true, and we want to just remember that. So like, let's say for example I have P implies Q. And so I have P implies Q, and what we know is that this conditional argument is going to be true if and only if the conclusion of the argument is true when the hypothesis is true. So if you remember the truth table for P implies Q, you know that if P is true, we have to have true implies true. Okay? Right? We start out with P being true, and then that forces Q to be true. If that's not true, okay, that is that P is true, true implies false, right? Makes the whole conditional false. And so that's going to become the basic idea behind valid arguments. In fact, that's exactly the idea behind valid arguments. An argument is only valid if, when the hypotheses are true, okay, then the conclusions are true. All right? So we'll write that out. So an argument is valid if the conclusion is true whenever the hypotheses are true. So when we look at something like that and we're asking ourselves, well, whether or not the argument is valid, if, say for example, the hypotheses are false, then we can't say anything about the validity of the argument. It doesn't matter whether or not the conclusion is false or if the conclusion is true. Just like with the conditional, right? Remember with the conditional, right, we could have false implies false. Or we could also have false implies true, and they both mean the conditional is still true. Well, in terms of a valid argument, we don't know whether or not, I mean, like, it doesn't tell us whether or not we have a valid argument if the hypotheses are false, right? And then whatever happens with the conclusions, we only want to concern ourselves with whether or not the conclusion is true given that the hypotheses are true, okay? So if the hypothesis is false, it does not matter what happens with the conclusion. Excuse me, what happens with the conclusion. What that means is that we start out with the assumption that the hypotheses are true. All right? So anytime we look at a proof, we're going to assume that the hypotheses are true instead of a proof. Okay? We call these things necessarily their assumptions. We say these are the assumptions, and the assumptions we assume to be true, because if they're not true, it doesn't matter whether or not our conclusions are false or the conclusions are true. We didn't start out with what we wanted to start out with in the first place. Right? It's like saying, well, if it is raining, then I'm going to bring an umbrella. Well, what if it's not raining? Who cares? I didn't say if it's not raining. I said if it's raining, I will bring an umbrella. And that's it. Right? Okay? We only care that if it's raining and I don't bring an umbrella, then I made an invalid argument. I've actually basically said, well, you know, what I just did is it doesn't work out, right? Okay? I've said, in the case that it's raining, I'm going to bring an umbrella. It started raining. I didn't bring an umbrella. My statement now is false. It's going to actually kind of like operate the same way. Okay? Not exact. It's not entirely identical, but that's basically the idea. So let's look at something. Let's look at like what we call a rule of inference, and let's look at how it works to think about it as being valid. Okay? So what we're going to do is we're going to structure an argument. Okay? And here's my argument. And I'm going to have some propositions. I'm going to have P implies Q. Okay, so P implies Q. and then I'm going to have P, and thus Q. Okay? And this one actually is something called modus ponens. So if I wanted to prove that Q was true, this Q statement is true, I'd have to know, one, that the conditional here is true, and then also in addition to that, I need to know that P was true. Okay? So like for example, what we'll see here is that we're going to assume that both of these are true, and it's going to force Q to be true. It's going to be forced Q to be true. Okay? So if we start out here, we're going to start out with P implies Q, and we know that that's going to be true under the instance in which we got true implies true. Okay? It's also going to be true when we have false implies true, and we also have false implies false. Great. Okay? Now, so that's for the conditional. These are what make the conditional true. So that's the conditional is true. Now, we also know that P equals true. So if I look at the three of these, right, now I'm going to make a comparison over here with the three of these. If I look, the only one that has P to be true, and notice P is over here in the conditional statement, that has P to be true is this true implies true. That's the only one. Okay? So if that's the case, then what I have now is I have that Q must be true. Notice that the other two, they don't have P being true. So consequently, we can't use them. We're only going to use the ones that actually match. And so consequently, since P is true and the conditional is true, that forces Q to be true. So Q must equal true. Right? Thus, the argument is valid. And that's what makes a valid argument. Right? If we know that the assumptions or the hypotheses for the argument are true, then that forces the conclusion to be true. Right? And thus we have a valid argument. Let's take a look at another argument. All right, so what we're going to do now is I'm going to look at the structure of this argument. So what we'll have here is normally you'll have a line, and that line is going to represent a divider between the hypotheses and the conclusion. Above the line, you'll have the hypotheses. Below the line, we'll have the conclusion. And these three dots, they mean therefore. So that's their meaning, they mean therefore. Okay? And what we want to do is we want to actually show that this argument right here, in fact, is a logically valid argument. So let's say, for example, we start out, and let's say that P is 9 is an even number. All right? And then we'll let let's let Q be 12 is an odd number. So if we look at this argument, what we're going to get is we're going to start out with, we've got not P, okay? And that's our first statement. And then we have now here, we're going to have not P implies Q. And then the last one is going to end up being not Q. And let's ask ourselves whether or not this actually is a valid argument. Okay? Is this valid? Well, if I start out and I say, okay, well, not P. We know that not P is true. That means P equals false. And we have P implies Q is true. So remember what we did there. For P implies Q is true, we know that we have to have true implies true. We have to have false implies true. And we have false implies false. We could do any one of those three. So we're going to only look at these two right here now because P we know equals false. Well, now, does that mean that not Q, because that's our conclusion, not Q must be true? Well, no. I mean, if we have this false implies false, okay, then Q equals false, So not Q ends up equaling true. That's one option. But then we have the other option, which is false implies true. And in this case, Q equals true, but then that means that not Q equals false. So if, okay, P equals false, which we know is true, is going to be the case because we got not P, okay, and Q equals true, then what do we have? We have not P equals true, and we have P implies Q equals true, but not Q is not true. In fact, it's false. So the argument is invalid. We have an invalid argument. Notice in this case, what we did is we assume that the hypotheses are true, and what happens as a result of that is we end up with a possible, although not certain, but possible conclusion that ends up being false. And when that's the case, we end up having an invalid argument. So what we want to look at now is we're going to look at these rules of logical inference. And so what the rules of logical inference are, is the rules of logical inference, they describe a set of logically valid arguments that can be used for proving the truth of propositions. They form the foundation for the work that we do in mathematics and also inside of computer science. You can kind of think of them as stepping stones to prove more complex propositions. So you'll notice as we work, we're saying P and Q and R, and these are just any kind of propositions. Any proposition that we want can be generated, can be, put together using like these particular letters. And then we have certain rules that we'll go through and we'll use them to combine them logically. Okay, and so if you imagine, like, say for example, we say things like if a number is prime, okay, and the number is even, then the number must be 2. So you'll notice that P is the number is prime, Q is the number is even, and then R is the number is 2. So you can kind of see that we string things together using those propositions. These rules of logical inference, they're going to tell us how it is that we can kind of build proof, how it is that we can build logical arguments, okay? And what you'll see is that as we start to do more and more work with logic proof, what we'll do is we'll prove new things to be true, and then we'll use those new things that we know to be true as the hypotheses or the assumptions for further conclusions, right? So what it'll be is it'll be like, okay, I know this is to be true, and I know this is true, and since these two are true, logic indicates that fundamentally this next thing must be true, right? And that's how we're going to end up building proof. So what we've seen before is we've seen these things that are these statements that are logically equivalent. That's kind of like identities. From a logical perspective, it's saying this thing and this thing, we can interchange the two. We can substitute one for the other. Now what we're going to do is something that's kind of similar, but it builds on the ideas of valid arguments. Okay, so what we're going to do is we're going to look at what are the most fundamental or the most standard logical arguments that we have, and which ones can we assume to be necessarily valid arguments as our assumptions. These are going to become like the building blocks. And in the process, we're going to look at how we show that they are in fact valid. It's going to make things, kind of easier for us. So we'll start out with the first one. The first one's called Modus ponens. And by the way, for students inside of my class, we have a list of these. In addition to that, what you'll see is that oftentimes you could find lists of rules for inference. So you don't necessarily need to memorize them, depending upon what you're doing. But I do want to make sure that you kind of see them and you kind of see where they're coming from. So this one has everything to do with the conditional. So this is the one we're going to start with P. That's our first assumption. And P implies Q. And then, therefore, what do we get? We get Q. Okay? And that's the conditional. The conditional states that if P is true, and P implies Q is true, then Q must be true. And we saw that one earlier on. That's the very first one that we actually proved. The second one is called modus tollens. And so modus tollens is like this. Modus tollens is going to utilize the contrapositive. So it's going to start out with not Q, and then it'll have the conditional, right? Not Q implies not P, and then what does that give you? Therefore, not P. And you kind of see that that's also going to work as a valid argument. It's basically the same exact statement as that we have for modus ponens, except with negations. So we'll assume not Q is true. We have that not Q implies not P is true. Okay, not Q implies not P is only going to be true. Okay, by the way, that means that Q equals false. If not Q is true, Q is going to be false. Then we'll have that not Q implies not P is either going to be, we've got true implies true. Okay, we have true, we have false implies true. We have false implies false. Okay, well, we know that Q is false. That means not Q is true. That's the first thing that we have there. So this is the only one that's going to work. And that implies, therefore, that not P is true. So not P equals true. And hence we are a valid conclusion. By the way, the logic assignment would have that that's P equals false. Since not P is true, that means P equals false. So if Q is false and P is false, we end up having this conclusion end up being true. Our next one is something called addition. So we have P is true, therefore P or Q is going to end up being true. So we're basically just going to add a proposition. Makes sense. We set P equal to true, and then we have P or Q equals true. When is that going to be the case? Okay, that's going to be when Q equals false or when Q equals true. All right, so this is going to be true. If we have P equals true, then P or Q will be true whenever Q is false or Q is true. Since that's the case, right, that means that P or Q is always true as long as P is true. Okay, so hence another valid argument. And we call that addition. Next up, we have something called simplification. And simplification is actually the exact opposite way around. All right, so simplification has P and Q, and then therefore P. Therefore P. So what you see here is P and Q equals true. That's our assumption. So that means P has to equal true and Q has to equal true. That's the only way that you get this to be the true statement, is both that are true. Well, automatically P is true. In truth, you can actually also say that Q must be true as well. But whenever we're doing logical proof, we want to make sure that the order of our propositions is correct, or that it matches our rules and our logical equivalencies. And in this case, Q is the secondary one. Okay, we're only really looking at the first one, which is our P, at least in our case. Okay. Next up, we have something called conjunction. Now, conjunction goes along with the idea of conjunction. Okay, so we've got P, we have Q, and therefore P and Q. It makes sense. P equals true, Q equals true, hence P and Q equals true. Because, well, that's how P and Q works. Okay, this is a rule of logic that P and Q will only be true if both P and Q are true. So hence we've got conjunction. We can also make that assumption. And the idea here is that I'm going to get P to be a true statement. I'm going to get Q to be a true statement. That means that their conjunction will necessarily also be true. The next one, it's got a fancy name, but it's not too terrible, is called the hypothetical syllogism. In algebra, this is very similar to something that we might call the transitive property. So we've got P implies Q, Q implies R, therefore P implies R. Now let me kind of show you, I'm going to write out a truth table in order to show hypothetical syllogism, and this is one of the ways that we can actually show logical validity as well. So what we'll do is we want P implies Q. So we've got these things here. I'm going to have P, Q, and R. I'm going to set up my logic table, my table this way. I'll have P implies Q. I'll have Q implies R. And then I'll have a third segment here, which is P implies R. And then here's my P, here's my Q, here's my R. I need a couple more here, 3 more. And we'll set it up. Oh, that was too many. 2 more. All right, so that covers everything that we need for P, Q, and R. Now we'll have P implies Q. I know that I'm going to have true implies true, so this is true. True, because that's true implies true. Notice right there. True implies false, that's false. False, then true, 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 and true for P implies Q. Then Q implies R. I'm going to get that's true there. I have true implies false here, so this is false. Okay. I have false implies true, that's true. False implies false. True implies true. True implies false, false. False implies true, so that's true. And false implies false, that's true. Okay? Now, what I need is I need both of these, because these are the hypotheses. I need both of them to be true. So I'm only going to focus on the ones in which they actually, both hypotheses are true. So that's that one there. Here's another one where both hypotheses are true. Last set, both hypotheses are true. And now, in order to have a valid argument, I need the conclusion, which is P implies R, to be true as well. So let's go through and do that. Well, P implies R, I've got true implies true, so that's true. That's the first section. The second pink one has false implies true, so that's also true. Then the third, false implies true, that's also true. Okay, and then false implies false, that's also true. So notice, for each one where I have both of the hypotheses to be true, the conclusion is also true. So what? That means that this is valid. If you think about this, this actually shows logically that essentially that if I start out with a hypothesis of P, and I know it gives me Q, right? That forces Q to be true, right? Because if P is true, then Q is true, okay? And then if Q is true, that forces R to be true, right? True to true, true to true. Or if P is false, okay, then what we end up with is that we end up with Q must end up being, if P is false, okay, we have that here, then Q could be true as long as R is also true, okay, or false, false, true, and then we could also have false, 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 all three of them is false, okay? And so it makes a bit more sense when a P, Q, Q, and R are all true in terms of the logical connection, right? Because you're like, okay, P is true, forces Q to be true, Q to be true, forces R to be true, so we can kind of just cut out Q, okay? But if I have the right combination of Q and R, for example, or P, Q, and R, then I can also end up having a true statement for P implying R as well, right? And that's because those conditionals are a little strange. Or, well, not strange, they have their own very specific set of rules. So that's the hypothetical syllogism. It's like that transitive property. And then we'll have the disjunctive syllogism. Excuse me. And that's P or Q. Then we have not P, therefore Q. And so basically what this is stating is that we've got P or Q is true. And remember, that's going to be true if what we have is P equals true, Q equals false. P equals true, Q equals true. P equals false, Q equals true. Okay? So that's when P or Q equals true is going to be the case. Then we know that not P is true. So that means that P equals false. So P is going to be a false statement. So what happens? If P is false, we've got to eliminate both of these choices, and we only end up with this here. So Q must equal true. And that's the rule of inference called the disjunctive syllogism. Basically what it's saying is that if you have an or statement, and one of the statements is false, the other one has to be true. And if you think about it, it kind of makes a lot of sense. It's very logical, right? I mean, if you think logically, that's how logic should work. Next up, we have the final one is what's called resolution. And so resolution is P or Q. And then we have not P or R. And therefore, Q or R. Okay? So in this case, we know that P or R is true. We have not P or R is true. Okay? And so let's actually set up a truth table here for this one, for P, Q, and R. Okay? And if you're okay with finding these truth tables already, then go ahead and fast forward. It's for those who maybe have not done a lot of it. And now we're going to have P or R. That's our first hypothesis. And then our second hypothesis, not P or R. And we need both of those statements to be true. So I also am going to need not P. So I'm going to put not P over here, just on the side. So we start with P or R. Anytime P is true, P or R is true. So this is true, 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 and true. And then anytime R is true, we also get true. So this is true, true. And then the only time that we have false is there's our false statements. And then we need not P or R. Okay, so not P or R. And so not P is going to be, these statements are going to be our false statements. And then we have, okay, true, 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 true. So not P or R is now going to be true whenever not P is true. So that's true, 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 true. Okay. And then if R is true when not P is true, so that gives me this one here is true. This one's true. And then I have false and false. And those two are false. Now, I only want to know when the hypotheses are true. So these are my hypotheses. So there it is, true and true, true and true, true and true, true and true. There's our 4 true and true statements. And now to prove logical validity, I'm going to go in and I'm actually going to test out my conclusion. My conclusion is Q or R. So Q or R, I got Q is true, so that's going to be true. Q again is, oh, that's false there, but R is true, so that's true. Q is true here, so that's true for my third, and then for my fourth, the R is true, so that's true. So you notice anywhere where my hypotheses are true, Q or R ends up being true as well. And we don't really care whether or not there are other ones where, Q or R might be true as well. It doesn't matter. All we need to know is that if these two statements are true, P or R and not P or R, whenever they're both true, then Q or R must be true as well. Okay? So hence again, for our resolution, we have valid. We have a valid statement. Notice resolution and disjunctive syllogism are kind of similar in some ways, or one leads to the other. We have P or Q. Okay? So one or the other of those must be true. Not P or R. One of those must be true. But these two can't be true at the same time. That's a contradiction. P and not P can't be true at the same time, so one of them must be false. So consequently, either Q or R has to be true at some point in time. And if you kind of think about it, it'll make some sense as you're working. So this is these rules of inference. For my class, we don't need to necessarily memorize them. If you're learning logic, you might want to. But what they definitely are is they're definitely a way for us to build logical reasoning. essentially they say to us, okay, if I know this is to be true and this is to be true, then my next logical step is this one right here. And the better that we can get with kind of like the feel of these rules of inference, the better it is that we will get with working with logic and also working with proof.